Hello there, everybody. It's Mr. Simon. It is Sunday, May 17th. I'm going to walk you through a little bit of what we're doing this week, but more in depth actually for what we're doing next week. So, going to our book, and obviously I shared these notes on Buzz. We started electricity this week. And electricity we divide into three different parts: electrostatics, electric current and voltage, and electric circuits. And electrostatics and current and voltage, the first two parts, the notes I shared on Buzz are pretty self-explanatory, I think, for the most part. And a lot of the notes are actually in your notes as is. So when you go through the first couple pages on the Buzz notes, there's only a couple of things added here and there and a few things highlighted. But a lot of the stuff with electrostatics, I think you already probably know. There's a couple of problems that we do along the way. And then current and voltage, uh, again, a lot of it's just guided notes. I have some problems that we did in there, introduce you to a couple different concepts. But the main thing that we're going to be looking at is current and voltage. Current is represented with I, measured in amps, short for ampere, and voltage measured in volts. On the following page, and you'll be getting to this hopefully this week, the week of the 17th through the 22nd, I believe. This equation, V equals IR, that is the F equals MA of electricity. That is the foundation of how we're going to do a lot of our circuit problems. So today, I'm actually going to take you through the last part of this unit on circuits. This would be, I believe, page 8 in your packet that I sent on Buzz, page 265 of our notes. So part 3 on circuits. We'll be starting this really the following week, the week after Memorial Day. We'll talk about this on Buzz. You'll notice there are two basic types of circuits, series and parallel. We'll talk about what those are today, and then what happens when we combine those two. But before we dive into the actual circuits, I want us to look at a little page I developed on page 269. I'm going to add a little bit more light here for us. So on page 269, it's an analogy I came up with years ago, and students have said they really like it. In fact, a lot of students in college will email me and say, Mr. Simon, remind me what that peanut butter and jelly analogy is. That's what it's known as a peanut butter and jelly analogy for circuits. This is on page 7 of the notes I shared on Buzz, page 269 from your actual book. So our analogy on circuits that I came up with. Well, let's take a look at what is a circuit first of all. Well, a circuit really has three main components. So you have the voltage source, which is really the energy source, and voltage is energy per charge. So when we're talking about voltage, we are talking about energy. A typical household outlet is 120 volts. Everything from your refrigerator to your television set to your hair dryer to a power drill gets plugged into a 120 volt outlet. You do have a couple outlets in your house that are twice that, 240. These are for large things, namely your clothes dryer and your electric range. Your air conditioning is probably hardwired right into 240 outlet as well, or 240 circuit as well. But everything else is a standard 120. We also can use batteries as voltage sources as well. They tend to have obviously less voltage, like 1.5 volts, 3 volts, 9 volts, etc. So the voltage source is the energy source. That's one component. Another component is what's going to use the electrical energy. So be it a light bulb, a toaster, a washing machine, a television set, some appliance load is going to use that electrical energy and convert it into some other form of energy. A light bulb is going to convert electrical energy into light and heat. My television set's going to take electrical energy and convert it into sound, light, and heat. My washing machine is going to take electrical energy and convert it into a mechanical energy of a motor that's going to spin around and around to wash my clothes. So all sorts of appliances will take electrical energy and convert it into other types of energy. And the third component are the wires. So what's going to take the actual electricity, which is current, which are electrons moving through a copper wire or a conductive wire, usually copper, to the appliance, and then takes the electrons back home. There's always two wires. Even if you see what appears to be one wire, there's at least two wires, one taking electrical current to the appliance, one taking it back home to the outlet. Sometimes there's a third wire in there, that little round plug on the bottom, that's a ground cord in case too much charge or current builds up. Well, obviously, drawing pictures of circuits, be them light bulbs, toasters, refrigerators, washing machines, television sets, gets way too complicated. So in engineering and physics, we have diagrams to represent things. So the voltage source is represented with three short and three long lines intermittently, like that. We square off the wires to make it easier to analyze. There are two different circuit resistor symbols. One is a rectangle, one are a zigzag line back and forth. What I tend to do, if I'm talking about actual little resistor components, for example, on a circuit board, whose jobs are to regulate the amount of energy going into different parts of your circuit board, I tend to use this symbol. If I'm looking at an appliance itself as a resistor that resists the current and then converts the energy into some form of energy, I tend to use those rectangles. But these are the type of pictures we'll be drawing, not these. And we're not so much drawing those as analyzing them. But here's the analogy I came up with that students have really liked over the years. It makes circuits really, really easy to understand. Voltage are the very tasty sandwiches. I chose peanut butter and jelly sandwiches because I love PB&J. And if you've never had PB&J on toast, you've got to try it. Peanut butter and jelly on toast is just, it's amazing. It's a PB&J stepped up a couple degrees. So try that. But voltage is the energy, and energy for us would be our food intake. So the voltage are the very tasty sandwiches. Current is literally the electrons zooming through a conducting wire. Again, a lot of wires are made out of copper. And there's billions and billions of electrons moving through those wires. Current is measured in amps. The symbol is I, and I draw current are the cars. So instead of electrons zooming through the wire, billions of them, we're going to look at cars driving down a road, something we're very familiar with. So the current are the cars measured in amps because they're automobiles. The resistors are the rest stops. Sometimes I'll say city, sometimes rest stops. Rest stops fits the letter analogy, and that's where we're going to eat our sandwiches. And the wires are all one-way streets. And the only rules are we have to eat some of the sandwiches at each rest stop, and we have to have all the sandwiches eaten up before we get back home. Remembering those things is about all you need to understand circuits. So going to page 8 from the notes I shared on Buzz, which is the same as page 265 in your notes, let's take a look at how a circuit problem is done. There are two basic types of circuits, series and parallel. Series, think of what the word series means. If you're watching the World Series, that's baseball. For those of you who don't know, the World Series is one game after the other. Or maybe you're watching a Netflix series and you watch one episode after the other. So if I wire resistors in series, I'm just wiring one right after the other. Here's my voltage source. I hook up a wire up to the first resistor, then a wire to the second, and a wire to the third, and a wire that goes back home. One right after the other. The other basic type is parallel. And parallel gets its name for the obvious reason. But what happens with parallels, we have intersections. So I'm going to get to that in just a moment. The bottom is a combination circuit. We're going to combine some seriesness with some parallelism. You're going to find out it's not that difficult. So series circuit, let's take a look at what's going on here. And the main equation we are going to use in circuits is Ohm's law, V equals IR. That was on the previous page 264, the F equals MA of electricity. V equals IR, or as students like to say, VER. And VER gets applied to every resistor. So there's going to be V1 equals I1 times R1, and V2 equals I2 times R2, and V3 equals I3 times R3. That's the equation it's going to solve for all these little unknowns. And basically for circuits, that's what we're doing, is solving for unknowns. So I take a look at this circuit. I know I'm starting with 120 very tasty sandwiches. And technically that means every car has 120 sandwiches. I don't know how many cars are going on the trip yet. And I sub O means the original current or the original cars. V sub O is the original voltage or original very tasty sandwiches. Today we're going to have 3 rest stops. We're going to eat some of those sandwiches in each one. I like to look at each resistor, and anytime I see two of three things, I can say VER and apply V equals IR to that circuit. If I apply V equals IR to that circuit, I'm going to get two cars, two automobiles, 2 amps that are driving through rest stop 2, which means two cars had to come this way into that rest stop, which means two cars must have came from the first rest stop or the first city, which means two cars had to enter into the first city. And those two cars, after they drive through this second rest stop or second city, are going to take another turn and drive right into the third rest stop. And those two cars are going to leave the third rest stop and go right back home. And that's great because the amount of cars that go on the trip, the current, has to be the same amount of cars that comes back home. Well, I got 2 out of 3 things here. I can say VER. V3 equals I3 times R3. That gives me 30 ohms. And ohms are represented with the Greek letter omega, an upside down horseshoe. You can think of the ohms as the hours we're spending. So I spent 10 hours, two cars spent 10 hours eating 20 sandwiches at rest stop 2. Two cars spent 30 hours eating 60 very tasty sandwiches. More time spent, more ohmage, more voltage. More hours spent, more very tasty sandwiches eaten. Well, we packed 120 sandwiches. We ate 60 there. We ate 20 there. Seems to me like there are only 40 sandwiches left. And the rule is we have to eat all those very tasty sandwiches before we get back home. And there's another VER. V1 equals I1 times R1, 20 ohms, and our problem is finished. All the unknowns solved. You will note for series circuits, one right after the other, the current never changes because all those cars just keep taking a right turn, go through the rest stop, right turn. It's kind of like watching a NASCAR event. Everybody keeps taking the same turn. And the voltages all add up. So how many very tasty sandwiches I have to start with, I have to eat a little bit up at each spot. And all those are going to add up to the total amount of sandwiches. A parallel circuit is different because there's an intersection. So all these cars are going to leave home, go down this back stretch. All the cars, the current, the automobiles are going to come into this intersection, and some cars are going to take different turns. Just like you at an intersection, you can take a left turn, a right turn, or go straight. We're going to use the same voltage just to show you a couple interesting things. And if I look through what I'm given and what I'm trying to find, I don't know a whole lot to start with. But one thing that's interesting with parallel is regardless of how many cars go on the trip this day, you're only going to go through one rest stop. Remember, they're all one-way streets. So we can't drive through rest stop 1 and then back up through rest stop 2. No way, man, the current's coming this way. So regardless of how many rest stops or cities there are, my car that I'm traveling in can only go through one rest stop before it goes back home. And the rule is we have to eat all the sandwiches, which means if I go through rest stop 1, I got to eat 120 sandwiches. Maybe my friends went through rest stop 2, they have to eat 120 very tasty sandwiches. And maybe some of our friends who went through rest stop 3, they had to eat 120 very tasty sandwiches. So regardless of which way you picked, you ate all your sandwiches before you went back home. That's one of the few rules. Hey, I got a VER. V equals IR, man. V equals IR here gives me 3 amps or 3 cars that went through rest stop 3. V equals IR gives me 4 that went through rest stop 2. V IR here gives me 120 ohms of resistance there. So how many cars went on the trip this day? Well, if the cars are splitting up at the intersections and 3 cars went that way and 4 cars went that way and 1 car went that way, 8 cars had to go on that trip. And if we were in school, we'd actually be playing with these little circuit boards. Some of you might actually have these at home, these little snap circuits, and they work really well. For example, here's one of the situations. I don't know how well you can see this, but I have 3 light bulbs. I'm going to turn my lights off so you can see this. Turn this light off, and I'm going to hold down. Right, here's my batteries, my outlets. I'm going to hold this down, which completes the circuit. And I've got one light bulb right after the other. So watch what happens when I pull this down and I'm holding it down. You can see very dim lights. from the little current going through these little snap circuits. Each of these snap circuits just has a little wire in it, no difference between that and the wire. Notice with a series circuit, as I turn my light off again, those lights are pretty dim. Again, there. But watch this. I'm going to replace this with a parallel circuit. I'm going to take those same 3 light bulbs, take them right off of this circuit, pop that one off, pop that one off, pop that one off. Same 3 light bulbs. And I'm now going to put those in a parallel circuit. Notice the parallel circuit, the electricity is going and it comes through an intersection. It can take this turn, or this turn. I'm going to pop those same light bulbs in to complete these circuits and see what happens in parallel versus series. As I turn my lights on, how much brighter those are. Same light bulbs, wired in a different way. A lot brighter, meaning a lot more electricity, technically a lot more power and energy being used. So different types of circuits give different properties, and sometimes a series circuit is better, sometimes a parallel circuit is better. One thing about a series circuit is if one of these, let's call these light bulbs, burnt out, it would disrupt the path and no current can go. We'd have a traffic jam and no cars can drive. And appliances need cars, electrons to move. That's why sometimes your holiday lights, if you have holiday lights, one bulb goes out and the whole string goes out. And you don't know which one was the faulty bug, and you got to go through one by one. It's a real pain in the patootie. But with a parallel circuit, if one of these burns out and has a traffic jam here, the cars can still go the other ways. And that's why you can buy some holiday lights where if one bulb goes out, the rest of the bulbs still work. A lot more friendly to the person who wants to put up lights, but as you saw with the little demonstration, the lights are brighter, which means it's using more electricity. A combination circuit combines both parallel and series circuits. What I love for you to do right now, if you've got the courage to do so, is pause the video and see if you can solve for the unknowns here. If you get stuck, just hold on, because obviously you can unpause it and come right back. So pause the video if you get a chance. Try to solve for those. Now, as you unpause the video, let's take a look at what we know and what we're trying to find. So notice there are 4 rest stops or 4 cities, but the car that you're in one of these 8 cars. And by the way, all the numbers don't have to be even. You can have 8.5 amps and 117.3 ohms and 62.5 volts. We try to make them nice numbers, but they don't have to be. So we have 8 cars going on the trip, original current. All 8 cars got to go through the first city, but then they're going to split up. You got to pick one of those 2 to go to before you get back home. So even though there's 4 cities or 4 rest stops, you are only going to go through 3 of them. Well, because there's no intersections, all 8 cars are going to go through city 1 or rest stop 1. Then those 8 cars are going to come into this intersection. And I like looking at the cars first. I think it's easiest. So 8 cars going through this intersection. They're going to split up and split up, but then they're going to recombine coming back out of this intersection. So 8 cars have to go through the 4th rest stop, which is good because 8 cars are going to get back home, and the amount of cars that leave have to be the amount of cars that come back home. Well, I got a couple of VERs right out of the gate. V equals IR, 40 very tasty sandwiches eaten there, and V equals IR, 50 very tasty sandwiches eaten right there. Now let's take a look at what we have. Over here, I still have some things not solved for, but I can apply VER here and get 5 amps, meaning 5 automobiles or 5 cars. So the 8 cars that went into the intersection, 5 cars went that way, so 3 cars went that way. 5 and 3. They're going to recombine to form 8 coming back home. Since my friends that went through Rest Stop 3 ate 60 sandwiches, and I go through Rest Stop 2, I've got to eat 60 sandwiches as well. The amount of sandwiches you eat in parallel always stays the same. I've got a VER there for 20 ohms. And the only thing I have left is the original voltage. What I'm not going to do, I'm not going to take 40 plus 60 plus 60 plus 50, because I did not go through 4 different rest stops. I have to take a look at any one path. So let's say I went through rest stop 2. How many sandwiches did I eat? 40 plus 60 plus 50 is 150 very tasty sandwiches. And some of those cars, some of my friends went through the other city. They ate 40 plus 60 plus 50, the same 150 sandwiches. Circuits are like puzzles. And I tell students every year, you're going to love circuits. If you love puzzles, especially, you're going to love circuits. And they never believe me. And then every year when we work on circuits, a day or two later, students are going, hey, man, those are kind of fun. So what we'll do on Zoom is we'll work on a couple of these on page 266. I'd say try these on your own. The first 3 are just like the one we did last on the previous page, and this one's not a whole lot more difficult. We probably aren't going to get to equivalent resistance. I think we're going to run out of time, but I did put later on in the book, and I know some of you are going to love doing these, on page 274 and 275, some other circuit problems. So give those a shot if you want. They're not all that difficult. They get a little bit more difficult as you go along. The last couple over here on page 275 are a little bit more difficult. And maybe we can do those on Zoom. And just so you know, too, I put a fun little word search here because I know a lot of you like to do that. So that is our little talk on electrical circuits. I hope everybody's doing well. I miss you guys tremendously. I know a lot of you are missing school and your friends as well. But you know what? We're going to make it through this thing. So stay happy, stay healthy. As always, please join me on Zoom and email me with any questions or problems that you have. Hope you guys have a wonderful day and a wonderful week.